Next, we move to small scale fading that manifests itself in the form of multipath distortion. To understand this concept, we start with assuming no carrier wave. Take an example of a hiker who is climbing the mountain and the signal is coming to his mobile from multiple paths. In this example, we will consider three paths: a direct path, a reflection with a delay of 0.6 microsecond, and another reflection with a delay of 1.1 microseconds. Assume that the year is early 2000s and our hiker only wants to check his email or messages. We say that this is a low data rate scenario. This requirement can be satisfied with a symbol rate of 100 kilobits per second. Since we are considering binary modulation, our symbol rate is the same as the bit rate. The symbol time is then given by the inverse of this bit rate, and it is 10 microsecond. This means that the time interval over which a symbol is sent is given by 10 microsecond. Now, the first path was delayed with 0.6 microsecond and the second was coming with a delay of 1.1 microsecond. This 1.1 microsecond as compared to 10 microsecond is just around 10%. Let us see what is the effect of this phenomenon after the addition of these paths at the antenna of the receiver. This is the direct path. This is the one with the delay of 0.6 microsecond and this is the one with the delay of 1.1 microsecond. You can see here that while multiple paths are added, each symbol is largely adding to the same value and it is not interfering with values into the future. This is due to the low data rate scenario and we say that not much inter-symbol interference occurs. Let us say that the year is early 2010s now and the hiker wants to sit on the top of this peaceful mountain to watch YouTube videos. His data rate requirement has now increased to 10 megabits per second. Again, due to the binary modulation, the symbol rate and the bit rate is the same and our symbol time is given by 1 over 10 megabits per second, which is 0.1 microsecond. When will the second path arrive? After 0.6 microsecond. The third path after 1.1 microsecond. These are a significant proportion of 0.1 microsecond now, and if we look at this figure, the symbol time has become very short. The second path is still arriving after 0.6 microsecond. The third path is arriving still at after 1.1 microsecond. But the first symbol is now interfering with tens of symbols in the future. We say that the amount of inter-symbol interference has significantly increased and the same hardness channel has become harsh for high rate communications. This inter-symbol interference poses a significant challenge to the implementation of wireless communication systems at high rates.
To understand a wireless channel, I have made this flow graph which consists of three different paths. Let us study how it works. The multipath channel. The excess bandwidth of the root raised cosine filter is chosen as 0.5. There are 32 samples per symbol initially and the sample rate is 48,000, which means that the symbol rate is 1.5k. I have chosen two GUI labels so that we can see the samples per symbol and the symbol rate on the GUI itself. Now there are three delays of the three paths. The first path comes with a default value of 0, the same as the second and third path. Let us call it the direct path, the first multipath, and the second multipath to avoid confusion between path 0 and path 1. Their amplitude have been chosen such that the default value for direct path is 1 and the first and second multipath have the values 0. After the bits generation, we generate a pulse amplitude modulation waveform where these values are coming from the variables defined here, and we check the transmit spectrum through this frequency sink. Now delay 0, and delay 0. These are all actually the delay of the direct path, delay of the first multipath and the second multipath. Similarly, their amplitudes are defined here. There are two things about this flow graph I want you to note. One, we have not included any carrier wave here. This is due to the simplicity with which we can see the intersymbol interference arising from the multipath. In an actual passband system, obviously there would be a carrier wave involved, which we will see later. The second point is that I have chosen everything real. So the channels are coming with real coefficients, the waveform is PAM, so that everything can be seen on an actual real number scale instead of getting into the complex numbers and phases and the real and imaginary parts. After these delays and amplitudes, these paths are added together, the power is normalized, and the received signal is shown in time and frequency domain. Let us run the flow graph and find out how it works. So this is the output of the flow graph, and I have displayed the samples per symbol 32 and symbol rate 1.5K here through the Qt GUI labels described earlier. The delay of the direct path is obviously 0, and the amplitude is 1. The other two paths have been arriving with an amplitude which we will choose here. Let us start with some value of the first multipath, and here you can see with only one path, the signal which is arriving is exactly the same which is adding to the receive antenna. Now the two paths are adding in phase, giving some delay to the first multipath, and you can see the path is coming from a slightly different delay. In our case, for example, if the delay is 8, the samples per symbol are 32, I can say that it is arriving after the delay of a quarter symbol period. You will observe here that the received signal at the antenna, where the signal are being added, is not much different than what was transmitted. Let us increase the delay more, and the signal shape starts changing. You can see that the delay right now is half the simple period. So the arriving multipath, which constitutes of the direct and first multipath, is starting to disturb the cumulative form of the received signal. Although it is not much different either at this stage, but if we keep increasing, so now we are very close to symbol period. One symbol period is 32 samples, so we are 30 samples later. And we can see that the signal shape is being distorted. This is also visible from the transmit spectrum and from the receive spectrum. They are a markedly different shape. And what happens when the delays go past one symbol period? It starts exhibiting more and more intersymbol interference. Let us assign some amplitude to the second multipath, and we will see it rising. If we start giving some delay, you will see that these green lines, they show the second multipath, and it can go beyond several symbol periods in my settings. When this happens, the transmit spectrum and the receive spectrum are clearly very different, and it's not even possible to locate a pulse amplitude modulated waveform since it will be so much distorted. This is why the multipath pose a significant challenge to high rate wireless communication systems, but not as much to low data rate wireless communication systems, because low data rate implies that all these paths, they arrive very close to the actual direct path, and hence they did not distort the signal shape. This is clear from both the transmit and receive spectrum. They do not generate much intersymbol interference, which implies that one symbol at this point does not interfere with several symbols in the future. To view that effect, I will change the number of samples per symbol to 4 and run the flow graph again. In this case, we are talking about a high data rate waveform, 4 samples per symbol, and the symbol rate has gone from 1.5K to 12K. Let us assign some amplitude, and here clear PAM waveform is visible. With the first multipath arriving, it's not much different. And also you can see a high rate signal requires more bandwidth as compared to the previous stage. The delay is now 3/4 of a symbol period because there are 4 samples per symbol and we have 3 samples delay. It's coming close to a symbol period and starting to distort the signal waveform. This is visible from here and here as well because they do not correspond exactly to the same ones and zeros, although it's still ones and zeros. And after that, this is a clearly distorted waveform. And the important point is that lots of intersymbol interference is visible here. Why? Because a delay of 27 implies that one symbol will be with 4 samples per symbol will be interfering into 6th or 7th further. So here you can see that this symbol is actually visible here. So it's interfering around 1, 2, 3, 4, 5, 6 symbols into the future. And same goes for. So this symbol is visible here and so on. And once the third path is added, this clearly is a completely different waveform that arrives at the receiver. For a more clear view of constructive and destructive interference, let us add the first multipath with different delays. This is a 1 sample delay, a delay of 2 samples, a delay of 3 samples, and a delay of 4 samples. Now you can see the shape of the receive and transmit spectrum. And here you can see that there are points where our signal is being destructively added, and there are points where it is constructively added. Finally, the delay of the last path. In this case, there are 2 multipaths, but the delay of the last path as compared to the delay of the first path is known as delay spread. In our example, the delay spread is 93 samples, which is about 23 symbols.
Till now, we ignored the carrier wave to understand the intersymbol interference phenomenon. With the carrier wave entering the picture, this is the physical phenomenon and this is the signal processing viewpoint. The physical process is self-evident, 3 paths arriving at the receiver. As far as the signal processing viewpoint is concerned, a baseband signal is upconverted to passband and sent on a wireless channel. The question here is that why is a wireless channel in time domain shown with 3 impulses? Recall that convolution of a signal with a unit impulse is a signal itself. Since our same transmitted signal is arriving at the receiver, we say that it is convolved with a unit impulse. And it is convolved with a unit impulse with a different delay because this path is arriving after a little delay. The same goes for the third path, which has the largest delayed impulse. And after the down conversion at the receiver, we can see that these paths are interfering with each other in different manner, details of which we will see now. It is important to note that each multipath traverses a different route. However, owing to the large scale fading, over shorter difference in distance, there is not much change in their amplitude. However, the delays which arise from different path lengths have a profound impact on their magnitude, as we will shortly see. We can say that the 3 paths had 3 different amplitudes, rho I, and 3 different delays, tau I. After down conversion, these real amplitudes turn into complex amplitudes, the reason of which we will see next. First, we say that the delay spread, as the name says, is the delay of the last significant path. In this case, The delay spread is given by the time difference between the third path and the direct path. We can see it here.
In the previous flow graph, we did not include the carrier wave to show the effect of the symbols themselves, plus ones and minus ones, and how they add up to produce constructive and destructive interference. When the carrier wave is present, then the phase also comes into play in addition to amplitude and delays. Let us see how. Most of the settings in this flow graph are the same as the previous one, where the excess bandwidth is 0.5, there are 32 samples per symbol. The sample rate have changed to 40,000 and the carrier frequency is 10,000. Other than that, there are three paths, a direct path and two multipaths with their delays, and these are their amplitudes, which can be controlled through sliders. One major difference you see here is that after the bits generation, we do not have a PAM waveform block. Instead, we have a QAM waveform in passband, where these values are taken from the variables defined here. This is because we want to see the effect of carrier wave on the arriving signal. These are the three paths with delays and amplitudes, and let us run the flow graph. So there are 32 samples per symbol and the symbol rate is 1.25K. Here we can see that the arriving multipath consists of just one copy. This for the received signal, and these are the same. And the amplitudes of the first and second multipath are 0. Let us go back now and study the effect of this carrier wave. For this purpose, I remove the auto scale option in both oscilloscopes. Have a look at the carrier frequency. This is 10,000 Hertz, which implies that one cycle of this carrier frequency gets completed in 1 over 10K, which is 0.1 millisecond. 0.1 millisecond in terms of the sample rate 40K turns out to be 0.1 times 40, which is 4. So we expect that when we run the flow graph, we should see a constructive interference if the delay is 4 samples. The first thing you notice here is that this is from -1 to 1 and this is from around -2 to 2. So they are adding in phase, which is evident because there is zero delay for the first multipath as well with maximum amplitude. Let us make the delay of this first multipath to 4. You can clearly see that the waveform from -1 to 1, but the received signal where these two signals are adding in phase has a peak to peak swing of -2 to 2. This is called constructive interference. Now, if we go back to the flow graph itself, and we see that one cycle is getting completed in 0.1 millisecond, half a cycle will get complete in 0.05 millisecond. When we multiply it with the sample rate of 40,000, this implies that in two samples, we should see destructive interference. One, two. These are two different multipaths, and now they are clearly seen to be different. And once that happens, we can see that the signal is drowned out. The power of the transmit spectrum is also in time domain, this has almost become zero. This is what we call destructive interference due to the arriving phase. And here we can see the transmit spectrum has a relative power of -20 dB, while the receive spectrum has gone way beyond that. This was a little demonstration of the constructive and destructive interference when the actual carrier wave is included.
Delay spread signifies the channel length, and it is a very important design parameter in wireless communication systems. It is the first out of 4 fundamental quantities through which a wireless channel is quantified. Now we come to the point where we ask the question why the real channel gains rho I, which were just amplitude scaling, hence a real number, has turned into complex numbers. If we recall the same result we have used over and over again, a shift in one domain manifests itself as a multiplication of complex sinusoid in the other domain. So when there is a shift in time of these paths, this gives rise to complex sinusoids in frequency domain of the channel response. These are complex sinusoids rotating at different inverse periods, which are actually the time delays tau i's. Clearly, at the bandwidth of the channel, they have both I and Q components. The I component is given by summation rho I cos 2 pi fc tau I, and the Q component is given by minus summation rho I sin 2 pi fc tau I, where fc is the carrier frequency. Further derivations of this result can be found in any wireless communications text. Let us take an example to see why these path lengths hold such an importance. Suppose that the carrier frequency is 1.9 GHz and there are only two paths, direct path with an amplitude of 0.9, reflected path with an amplitude of 0.6, and the delays are 0 and 5 microsecond. Clearly, gamma naught equals 0.9 because cos 0 is 1 and sin 0 is 0. Now, as far as gamma 1 i's part is concerned, it is rho 1 cos 2 pi fc tau 1, which is 0.6, and gamma iq is minus rho 1 sin 2 pi fc tau 1 equals 0. We deliberately chose this example to make this 0. Now see what happens if tau naught, the direct path, stays the same, but the tau 1 is slightly different by just 2 nanoseconds. That is, channel length in time domain becomes 5.002 microsecond. Then you can see gamma is changed by a significant amount, by a difference of 2 nanoseconds. So the purpose of this example is to show that small variations in the wireless channel result in huge variations in the amplitude. This brings us to the familiar multipath constructive and destructive addition scenario. In this case, the two waves are adding in phase, so their amplitude and power has significantly increased. On the other hand, here the multipath are arriving with a slight delay and the signal is relatively drowned out. We conclude that the term to focus is 2 pi fc tau I. When the phase of each path completes a 2 pi cycle, that means fc tau I is 1 and fc equals 1.9 GHz implies that constructive interference happens when there is a change of 15.8 cm in the path length. However, for a change of just 7.9 cm, it results in destructive interference and the signal is wiped out. Many people find it convenient to represent this concept through vector sum perspective. This is the direct path with an amplitude and phase. This is the reflected path with amplitude and phase, and they can add together through vector addition and to get this resultant vector. This brings us to coherence bandwidth. It is a range of frequencies over which the channel frequency response can be assumed as approximately constant. So the coherence bandwidth of this channel, as we can see in this figure, is not very large. Why is it proportional to the inverse of the delay spread? We know that the delay spread is given by the delay between the last significant path and the direct path. This is because the rotation rate of these complex sinusoids depend on these delays. So if these delays are large, then these rotation frequencies are large and the coherence bandwidth will be small. On the other hand, if these are very small values, then these complex sinusoids will be rotating with a very small frequency and the bandwidth over which the channel response can be assumed constant will be large. Coherence bandwidth is the second out of four fundamental quantities through which a wireless channel is categorized. From this perspective, channel can be divided into frequency flat fading and frequency selective fading. When the delay spread is small, data symbol values are almost the same. This is what we saw earlier. So all the multiple paths arriving within a very short time of each other. These impulses arising from the multiple paths, they are so close to each other that they can be intermingled into one common factor. We say that the channel response is a single impulse whose magnitude and phase depends on the vector addition of the phases of these paths, which can vary from very small to very large. This condition, delay spread is less than 0.1 tm, can now be inverted to get the frequency domain condition. Coherence bandwidth is the inverse of this delay spread. So we said the coherence bandwidth is significantly larger than the signal bandwidth, which is, we can see here in this example, the signal is narrow enough that the channel at this stage can only be considered as a single gain. The name flat comes from the fact that the channel is almost flat within the bandwidth of the signal. This gain corresponds to the gain of this impulse. A frequency selective fading is the other phenomenon where a lot of inter-symbol interference occurs. So the channel response shows several impulses arriving at different times. We say that the delay spread is greater than the symbol time, and this condition results in frequency selective fading. Going into the frequency domain, coherence bandwidth is less than the signal bandwidth. The inverse of this is coherence bandwidth, inverse of this is the signal bandwidth. Recall that the coherence bandwidth is defined as the range of frequencies over which the channel can be assumed nearly constant. When the signal bandwidth is larger than the coherence bandwidth, then some part of the signal experience a good channel, while other parts experience a bad channel.